Welcome to this video. The title of this video is Production of X-rays. X-ray tube. An X-ray tube is a vacuum tube that converts electrical energy into X-rays. X-rays are used in imaging and therapy applications. X-ray tube components. First, heated tungsten filament cathode. This element produces electrons when heated. Tungsten target. This is struck by electrons, producing X-rays. High voltage source. This provides the energy to accelerate the electrons from the cathode to the target. Evacuated envelope. This encloses the tube and removes air to prevent electron collisions. Copper anode. This helps dissipate heat produced by the tungsten target. X-ray production. The high voltage source accelerates electrons from the cathode to the target. When the electrons collide with the target, X-rays are produced. The anode absorbs most of the heat generated, preventing the target from melting. Continuous spectrum. The continuous spectrum is produced when high-speed electrons are rapidly decelerated upon striking a metal target. This process emits X-rays over a broad range of wavelengths. Starting from a minimum wavelength, which depends on the applied voltage. First, thermionic emission. The filament is heated, releasing free electrons into the vacuum. Second, electron acceleration. A high potential difference is applied between the filament and the anode. This accelerates the electrons, giving them high kinetic energy. Third, deceleration at metal target. The high-speed electrons hit the metal target and decelerate rapidly. During this process, the lost kinetic energy is converted into X-rays that have a continuous range of wavelengths. Next, X-ray wavelength range. The continuous spectrum includes X-rays of all wavelengths above a certain lambda minimum. Lambda minimum depends on the voltage applied. Higher voltage results in shorter lambda minimum. For dependence on electron energy, the higher the speed of electrons, the greater the range of wavelengths emitted, but the intensity peaks in a specific region. Then, efficiency of X-ray production. Most of the electron's energy becomes heat, requiring cooling of the metal target to avoid damage. Characteristic spectrum. When high-energy electrons collide with atoms in the target material, they can eject tightly bound inner shell electrons, especially from the K or L shells. This creates a vacancy in the inner shell, leaving the atom in an unstable and excited state. To stabilize the atom, electrons from higher energy levels drop into the vacant lower levels, releasing energy specific to the element. This process leads to the production of X-rays with specific wavelengths, forming the characteristic spectrum. When an electron from a higher shell fills a vacancy in the lower shell, the energy released is emitted as an X-ray photon. The energy corresponds to the difference between the two shells' energy levels, leading to sharp peaks in the X-ray spectrum. The peaks such as K-alpha and K-beta represent transitions like L shell to K shell and M shell to K shell respectively. These sharp peaks are unique to the target material, helping identify the element based on its characteristic X-ray spectrum. Next, we proceed to case study. From the question, we are asked to calculate the energy of the X-ray photons in electron volts and the wavelength used. The energy of the X-rays photon can be calculated by using the formula E equals EV. Next, to calculate the wavelength, Planck's equation, E equals hf or hc over lambda is used. After rearrangement, we get lambda equals hc over E, substituting the values to get the wavelength. These are the references used in this video. Thanks for watching.